You know, for centuries, some of the smartest people on the planet have been chasing this one single idea, an elegant theory that could explain everything, all of reality. But what if that entire chase, this hunt for a theory of everything, is, well, just completely wrong? Today, we're going to dig into why the universe might be way more interesting than that, and why that one ultimate theory, it might not even exist.
I mean, really think about that. Could you have one formula, just one set of rules, that explains everything from the moment of the Big Bang all the way to how our own brains work? It's the holy grail of physics, right? The absolute dream. But, as we're about to find out, reality, it has some other plans.
So first, let's just get into what this dream is all about, because it's a really powerful, really seductive idea that has been the engine for science for hundreds of years. This belief that if we just dig deep enough, we're going to find the master blueprint for the entire cosmos. This quote, from way back in the 1820s, just nails it. It's this idea of a perfect clockwork universe. The dream that if you could just know the position and speed of every single particle, you could predict the future with 100% accuracy. This big idea has a name, reductionism.
And the logic here, it makes a lot of sense, right? If you want to understand a car, you look at the engine, the wheels, the transmission. So if you want to understand the universe, you just have to find its smallest, most fundamental pieces, the tiniest atoms, and figure out the rules they play by. Simple.
And that's the ultimate promise, isn't it? Find the basic Legos of reality, learn how they snap together, and bam! You can, at least in theory, build everything back up from the ground floor. A star, a planet, even us. It's an amazing vision, but it runs headfirst into a wall, a quantum wall.
Okay, so now we're going to zoom in, way in, down into the totally bizarre, counterintuitive world of the very, very small. Because this is where that nice, neat, clockwork dream of reductionism starts to get really, really weird. So we usually picture a particle like a tiny little billiard ball, right? Solid, predictable, with its own set properties. But quantum mechanics comes along and tells us, nope, not even close. A particle, or a quanton as some call it, isn't a solid thing. It's more like a fuzzy cloud of pure potential, and its properties completely depend on how and if you're looking at it.
Okay, check out the single photon experiment. It's mind-bending. You fire one single photon, one particle of light, at a screen, and you give it two possible paths to get there. If you don't watch which path it takes, it acts like a wave and somehow magically takes both paths at the same time. But the second you try to measure which path it took, it snaps into being a particle and picks just one. The very act of looking at it changes what it does.
This totally bizarre behavior is called superposition. And what it means is that before you measure it, that particle isn't in this place or that place. It's kind of in a hazy mix of all its possible states at once.
So here's the kicker. The so-called fundamental building blocks of our universe, they're not solid, reliable Legos at all. They're slippery. They're based on probability, and their whole identity is tied to their context and whether or not something is observing them. You just can't build a predictable clockwork universe on a foundation that's this fuzzy.
And this is the turning point in our story. If you can't build the universe from the bottom up, then how does all this complexity we see happen? Well, it turns out we need a whole new principle, a new way of looking at things. And that principle is called emergence.
This quote from the physicist P.W. Anderson, this is basically the heart of this entire explainer. What he's saying is, look, just because you know the rules for one tiny particle doesn't mean you have any clue what a trillion of them will do when they get together. At every new level of complexity, totally new rules can just appear.
And that is emergence. It's the simple but profound idea that the whole can be way, way more than the sum of its parts. Think about it like this. You can study a single H2O molecule forever, but you will never ever find the property of wetness. Wetness only emerges when you have a whole bunch of those molecules together.
So let's see how this thing actually works. Because emergence isn't just some weird quantum idea. It is a fundamental rule that organizes our entire world, from chemistry all the way up to traffic jams. And we're about to see how the big picture, the whole system, can actually reach back down and change how its own individual parts behave.
Okay, this is a perfect example. Look at these two molecules. They have the exact same parts, 3 carbons, 8 hydrogens, 1 oxygen. The exact same formula. But arrange them one way, and you get propanol, a liquid alcohol. Arrange them a different way, you get methoxyethane, a gas used in aerosol sprays. Same parts, totally different things.
And what that shows us is something really crucial. How the parts are arranged, the structure, the organization is often way more important than what the parts themselves are actually made of. The pattern of the whole system is what dictates the result.
Or think about traffic, right? The laws of physics for a single car are perfectly symmetrical. It can turn left just as easily as it can turn right. But once you put millions of cars together into a traffic system, a totally new, unbreakable rule emerges: drive on the right. The behavior of the entire system now forces a rule onto every single car inside it. That's called downward control. So, let's just recap the big ideas here with emergence. First, the whole is genuinely more than just all its pieces added up. Second, when you scale up and get new levels of complexity, totally new rules and behaviors can pop into existence that just weren't there before. And finally, these bigger systems can actually impose rules back down on the very parts that make them up.
So, what does all this mean for that old dream of a theory of everything? Well, it means we have to completely change our picture of how science works, and maybe how reality itself is structured.
You see, the old reductionist way of thinking was that science is this neat pyramid. You've got physics at the very bottom, the fundamental layer, and that supports chemistry, which supports biology, and so on up the chain. But this whole idea of emergence just shatters that simple picture.
The reality is so much cooler. Science isn't a pyramid. It's more like a series of interconnected but also independent levels. Sure, the laws of chemistry emerge from physics, but you can't use particle physics to predict a chemical reaction. And the laws of biology emerge out of chemistry, but you are never going to derive the theory of evolution from the periodic table. Each level has its own valid, emergent rules that work on their own terms.
And that, right there, leads us to our final, unavoidable conclusion. If every level of reality has its own special rules that you can't predict from the level below it, then there simply cannot be one single theory that explains everything. That beautiful old dream, it's over.
But you know what? Instead of being a letdown, this is actually incredibly exciting. It means there isn't just one final frontier for science to conquer. There are infinite frontiers. It means that huge, groundbreaking, novel discoveries are waiting to be made not just in particle physics, but in chemistry, in biology, in neuroscience, everywhere. The universe isn't some simple puzzle we just have to solve. It's an endless, unfolding source of emergent complexity and, honestly, wonder.